Welcome back. This is Ink, and in the last problem, we took the average power and the energy of a signal x of t equals to the exponential e of negative 2t, and that was bounded by the unit step signal u of t. Because of the envelope, which is u of t, that energy was a finite energy, and for such a class of signal, when we have the energy less than infinity, the average power was zero. In this case, this signal x of t is not bounded by anything, thus we have to integrate over a infinite time interval. And if we integrate over an infinite time interval, it must be that we will get a infinite amount of energy. And when we have a finite amount of energy, we have an average power of zero. So thus, with an infinite amount of energy, that power, the average power of that signal must be greater than zero. In this case, we know that we're going to integrate over a infinite interval. So we know that without even going through the problem, that the energy is going to equal to infinity. But as always, we want to show that. So there's two important things for this signal. We know that j squared is equal to -1. We know that Euler's identity, j theta, is equal to cosine. We just let you just use theta without parenthesis, and that is equal to j sine theta. Oh, I like using parentheses. Okay, we know that in both equations we have to take the absolute value of x of t squared. We know if we take the absolute value of this expression, is going to equal to 1. And that is not the absolute value. I think in the first problem, I said it was the absolute value, but it was the magnitude of that signal when I think about it. So that's going to equal to 1 because if we have, say for this expression, if we have the magnitude, so that's cosine, let's just say x squared, which is cosine squared. We know that j squared is equal to -1. Negative don't count because the sign is going to be squared either way. Negative sign squared is a positive value, right? So that's going to be y squared. And we know that cosine squared plus sine squared is equal to 1 from the trig identity. So that is equal to 1. And we know that, the square root of 1 is 1. We could also say that 1 to the half, and then at the magnitude, they say we should square that. And if we square that, we get 1 to 1. And we know that 1 to anything is still 1. 1 to the power of anything is still 1. So we get those out the way. So we know that the magnitude square is going to be 1. So we can put that here. And that is equal to 1. Now we can approach the problem. We know that the energy is going to be infinite because we're integrating over a infinite time interval. So we can say the energy for the signal is the limit at which t approaches infinity. And if we integrate from negative infinity to positive infinity, and in that integration we have 1, we know that that's going to be, in this case, just let's say it's going to be positive infinity minus a negative infinity, which is plus infinity, and that's going to equal to infinity. So thus the energy is equal to infinity. Not sure if I went too fast, but basically what I'm saying is negative infinity to infinity 1 dt. That is, let's use t, that is t, negative infinity, positive infinity, that is equal to negative infinity minus a negative infinity, which is equal to a positive infinity. So this goes to a plus. And that's basically what I was saying. So now that we have the energy, we know that we have to have some power greater than 0 because this is a second class of signal. The first video had the class of signal at which we had a finite energy. Thus, we have a 0 average power. So now we can find the power. and that is the expression to the right at which the limit approaches the limit as t approaches infinity, 1 over 2t. We know that this expression right here goes to, in this case, 1. And if you integrate it, well, not 1, it goes to infinity once you integrate it. So we can say that this, let's just put it there, it's times infinity. And this is going to be t approaches infinity. That's going to be infinity over 2t. And as t approaches infinity, this expression right here goes to infinity over infinity, because 2 times infinity is still infinity. Infinity over infinity, that's 1. And we can see that 1 is greater than 0. So in this case, the average energy, well, not the average energy, energy for the signal is equal to infinity. And thus, the average power must be greater than 0. And in this case, it is 1. And that's how we do this problem. I'll do 2 more problems for energy and power, average power. However, I'll do those in discrete time. These are continuous time. Notice the variably independent variable t. And yeah, so look out for those. I might do them today. I'm not sure, but see you in the next video. Bye.